All right. So today we're covering program memory. And program memory is something you've already dealt with. You've had to do it. In Lab 3, you did a lookup table. It was in program memory. Nothing too crazy there. But in C, we haven't really talked about it. And you may not have thought about it in Lab 4, but those lookup tables that you created, where do they live? Three was they only lived in program memory. But in Lab 4, you're right, we didn't do anything special to put them in program memory, so they must have existed in RAM. But RAM is volatile. We lose data when we power off. But I don't know if any of you unplugged your boards and plugged them back in. It still worked. So that says that the numbers must have been in ROM. So what I've got set up here, this is based heavily on the AVR GCC lib documentation. In fact, there's sample data I just copied out. But what I've done here is I've made this two-dimensional array. It's just got numbers in it. It's 10 by 11. Okay, each one of these is 8 bits. It's just going to send some data. And all I've done is say, hey, let's send these out to port D. And it sends it out. And if I were to actually build this, I do have one of our boards in class today for various demos, it would work. All right, if I compile it, though, here's where things get interesting. It compiles, and let me just take this and zoom in on it it tells me that I've used 110 bytes of data memory. It says, okay, your program memory is 300 bytes. Your data memory is 100 bytes. So what we've got here is a case of double counting. 100 of these bytes are that array. So this array is stored in RAM, 110 bytes worth. Everything else is the stuff we've meant to see in the past. But also, it's reserved in RAM. So nothing else can use that 110 bytes, specifically because we made it global, so it always has to exist. And if we go and look at our listing, this is the next thing I want to show you. We'll go into our listing file. Vector table should be familiar at this point. Okay, no interrupts being used here. But there's a new piece that has come into existence, this do copy data. In short, it loads up address 100 and does a bunch of loads from program memory and stores into data. So what it's doing is it's copying. It's copying from program memory into RAM. And it does that, let's see, 110 times. 6E is 110 times. This is a fairly standard procedure that exists. Do copy data. Takes anything that's globally going to be in RAM and copies it from ROM into RAM. So, for those who just came in, we've got this block of memory. And it is stored in RAM, has to be, because it's assigned at startup. But the first thing that the code does is copy it into RAM. So we have 110 bytes of RAM, and also it's stored in 110 bytes of ROM. So it would be nice if we didn't have to have this double counted against us. All we're doing is accessing a byte at a time. Really, we only need a register. We don't need any data memory to do this if we could just access it from ROM. So if we were in assembly... Ooh. Is your phone okay? Okay. If you could access it in assembly, how would you access this in assembly? What kind of an instruction would you use? What instruction do you use to access program memory in assembly? LPM. There is no LPM construct in C, so we need to do a little bit more, okay, to talk about program memory. So go over to the web here. If you go to the AVR libc documentation, there is no internet connection. There is, oh, actually I saved it all because I knew I was going to have this problem. there is a file called program space, and it has a whole lot of stuff inside of it. Let me just colorize this for you, program it in C. It defines a whole lot of things to help you access data in program memory. The most important is this decorator. It decorates any instantiation of data. If you declare it as Progmem, the C compiler is smart enough to know to only put it in program memory. So here's how we modify this code. I have some pre-written code that's just going to modify this ever so slightly. All we need to do to tell the compiler to put this data in program memory is twofold. First, you have to decorate it with the program memory decorator. Say, unsigned char, my data, blah, blah, blah. Put it in program memory. The other thing you have to do is tell it const. Const means it's a constant. It's not going to change. It's read-only. All of these things are what the program memory are. You can't change it. It's read-only. So by adding this, again, going back to where we were, we started with unsigned character, my data, two-dimensional array. Now we have const unsigned data, two-dimensional array, program memory, in that order. So now it's in program memory. However, because it's in program memory, we have a problem now. We can't access it the way we did before. Here we just said my data sub j sub I. That's how we access any two-dimensional data. It's very simple to modify this to pretend that it's in program memory, or to use it as if it's in program memory. First thing we have to understand is, what is the size of every element in my data? You're right. Program memory is 2 bytes wide. That's not what we're talking about. How big is the data inside of this two-dimensional array? Nope. That's how many bytes are in it. There are byte-sized chunks. And it's only 120. It's just 120. 11 times 10. Yeah. No. So 110. So each one of these pieces of data is 8 bits wide. That's a byte. So one of the things you'll find is there are also a bunch of function-like macros. Program, read byte, read word, read dword, read float, read pointer. Byte is 8 bits, word is 16. Dword is a 32-bit quantity. So if we want to read a byte from somewhere in program memory, all we have to do is take this, okay, and you start by just putting that down. You're going to put the whole thing in parentheses. Can I make this any bigger? Put the whole thing in parentheses, and you want to say the address of that. That's the first step. Then you take this and you put it inside of that argument. You say pgm underscore read byte, because we specifically want a byte. And it goes like that. That's it. That's all you have to do. Just take your standard array access and surround it by an ampersand and a program read byte, because read byte reads from a memory location. So you have to say, give me the address of this byte in program memory. Now, I don't want to leave that here because I already have it here. So I've said const program memory, and now down here I say program read byte from my data sub j sub I. When I'm compiling this, just as a reminder, I use 110 bytes of program data memory and 312 of program ROM. Obviously, there's less RAM because I'm 5% full here of RAM, whereas with 300, I'm only 1% full on ROM. So if I change this, now where's my face? What I've done, so that you're aware of this, what I've done is I actually have 5 different C files here that I'm going to be going through to show you what's happening. Only one of them is set to compile. I've got the properties of that. This one says compile. So to go to the next example, I'm going to say none. Click on the next example and say I want this one to compile. Then when I rebuild it, it'll compile that C file. Okay. So I won't show you that ever again, but just know that that's what I'm doing. We're going to be talking a lot about cute little tricks that happen inside of Atmel Studio. So here it is. This is the money shot. If I go paste this in now, I'm using 290 bytes of program memory and no bytes of data memory. So by putting all of that stuff only in ROM, I've saved in two places. I've saved both in ROM and in RAM. The reason the RAM savings, that should be obvious. We're no longer copying data into RAM at the start of the program. In fact, if you look at the listing file, you'll see that there is no copy data. It's not there. It doesn't exist anymore because we don't have to copy any data into RAM. The reason for less program memory is because we don't have that copy routine. That's what's missing. We don't have the copy routine. Everything else is there, but we no longer have a copy. And if we go and look at the listing file right around here, you can see that it sets up Z somewhere up here and does an LPM. And then I think it updates. Yeah, it looks like it's updating Z a couple of times. Okay. But it does use an